Linear equalities are mathematical statements that compare the values of linear expression using equality symbols such as less than, greater than, less than or equal to, or greater than or equal to. They represent relationships between variables and provide a way to describe a range of possible solutions. Let's consider a simple example to understand linear equalities. Suppose we have two variables, x and y, and we want to find all the points that satisfy the following equalities. 2x plus 3y less than 10. To graph these equalities, we can start by rewriting it as an equation. 2x plus 3y equals 10. Next, we choose a test point that does not lie on the line. 2x plus 3y equals 10. For simplicity, let's use the origin as the test point. We substitute those coordinates into the inequalities. So 2 plus open parenthesis 0 plus 3 plus open parenthesis 0 is less than 10. Since 0 is less than 10, this statement is true to shade the side of the line that contains the test point. In this case, since 0 is less than 10, the side below the line represents the solution to the inequalities. The graph of these linear equalities is a region below the line 2x plus 3y equals 10. Any point in this shaded region, when substitute into the inequalities, will produce a true statement. It is important to note that the boundary line itself is not part of the solution. The solution consists of all the points below the line. If the inequality symbol had been less than greater or greater than or equal, the boundary line would have been included in the solution. In summary, linear equalities allow us to describe regions in the coordinate plane where certain conditions are satisfied. They are essential tools in various fields such as economics, optimization, and system analysis, enabling us to represent, constrain, and find feasible solutions.
Geometry of linear programming. The geometry of linear programming involves understanding the geometric interpretation of linear inequalities and the concept of flexible regions in relation to optimizing a linear objective function. So linear programming is a mathematical technique used to find the best possible outcome in a situation with multiple constraints. In linear programming, we work with a system of linear inequalities, also known as constraints, that define boundaries or restrictions in the flexible solutions. These constraints are typically represented as linear equations or inequalities involving variables. So each constraint can be visualized as hyperplanes in a higher dimensional space where the variables represent the axis. The flexible region is the intersection of all the constraints, which forms a convex polytope or a convex flexible set. So this region represents all the possible combinations of values for the variables that satisfy the given constraint. The flexible region is bounded by the constraint hyperplanes and can be visualized as a geometric shape in the variable space. To optimize a linear objective function within the flexible region, we seek the points or points that maximize or minimize the objective function while still satisfying all the constraints. So the objective function is typically represented as a linear equation and its contours from parallel lines in the variable space.
So the optimal solutions in linear programming is found at the extreme points of the feasible region. These extreme points are the vertices or corners of the polytope and represent the boundary values that yield the best objective function value. Since the feasible region is convex, any point within the feasible region can be expressed as a convex combination of its extreme points. So the graphical representation of linear programming often involves plotting the constraint, the feasible region, and the objective function. So by analyzing the geometric relationship between these elements, we can determine the optimal solutions and the corresponding values of the variables that achieve the best outcome. In summary, Usually, the geometry of linear programming involves visualizing constraints as hyperplanes, representing the physical region as a convex polytope, and optimizing the objective function at the extreme points of the physical region. So, understanding the geometric interpretation of linear programming helps in formulating and solving optimizing problems effectively.
Linear programming, or LP, is a mathematical technique used to optimize, maximize, or minimize a linear objective function subject. Consist of linear constraints, it provides a systematic approach to decision making in various fields, including operation research, economic, engineering, and finance. In a linear programming problem, we aim to find the best possible solution given certain constraints. The problem consists of three key components: decision variables, objective function, and constraints. So the decision variables, these are the unknown quantities we want to determine. They represent the quantities of values that we have to control over and need to make decisions about. Decision variables are typically denoted by symbols like x, y, or z. Objective function. This function defines the goals or objective of the problem. It is a linear equation that we seek to maximize or minimize. The objective can be expressed in terms of the decision variables and represent the quantity we want to optimize, such as profit, cost, time, or efficiency. The objective function can be linear meaning it is a sum of terms involving the decision variables, each multiplied by a constant coefficient.
Lines represent the limitations or restrictions imposed on the problem. They are linear inequalities or equations that define the feasible region within which the decisions variable must satisfy. Constraints can be represent limitations on resources, capacities, time, budget, or any other relevant factors. Each constraint relates the decision variables and coefficients to a specific limit or requirement. The goal of linear programming is to find the value of the decision variables that optimize the objective function. While satisfying all the constraints, the feasible region is the set of all possible combinations of the decisions variables that satisfy the constraints. The optimal solutions are the values of the decision variables that achieve the best objective function value within the feasible region. Linear programming problems can be solved using various algorithms such as the simplex method or interior point methods. These algorithms iteratively explore the feasible region to determine the optimal solution. In addition to graphical methods, specialized software tools are commonly used to solve complex linear programming problems. Efficiently, linear programming finds applications in diverse areas including production planning, resource allocation, portfolio optimization, transportation logistics, network optimization, and many others. It provides a powerful mathematical framework for making optimal decisions in situations involving multiple constraints and objectives.
Max, I just stumbled upon an ancient scroll that speaks of a legendary treasure hidden within the realm of mathematical optimization. We must find him.
Treasure? Hidden within mathematical optimization? This could be an extraordinary adventure, but we need some kind of plan.
Did someone say mathematical optimization? Count me in. I've been working on algorithms that could help us crack this puzzle.
I've been researching the ancient civilization route to possess this treasure. It seems they were mastered of logistics and optimization. I can help navigate our way.
Treasure, you say? Well, I can negotiate with anyone, even ancient civilizations. Let's make sure we get our fair share.
Alright, team, we have our objective. The treasure awaits, but it won't be easy. We will encounter obstacles and challenges along the way. Lily, what does the scroll say about first step?
It says we must solve a series of linear inequalities to unlock the path to the treasure.
I have just the algorithm to solve those linear inequalities efficiently. Let me input the equations and constraint.
So while Alex works on equation, I use geometry concept to visualize the visible region. We can plot our cars accordingly.
And I'll use my negotiation skills to convince any gatekeepers or guardians we encounter to let us pass without troubles.
This is it. The path indicated by our calculations and maps leads us here.
The numbers don't lie. This is the optimal route to the treasure.
The ancient civilization mastery of optimization truly shines in the design of this entrance.
And now it's time for my negotiation skills to come into play. Let's see if we can gain access to the treasure chamber without triggering any traps.
We did it! The treasure is finally ours.
All thanks to the power of mathematical optimization.
The ancient civilization wisdom and our teamwork made this possible.
And my negotiation skills ensured we left with more than just a treasure. I managed to reshare valuable artifacts and knowledge from the ancient civilizations. We've not only unlocked the treasure, but also expanded our understanding of optimizations.
Emma, your negotiation skills were crucial. It's amazing how our collective expertise brought us this far.
This adventure has been a true quest for mathematical optimization, transcend time, and connect us to ancient civilizations. This experience has reinforced my passion for the subject.
It's fascinating to see how mathematics and optimization transcend time and connect us to the ancient civilizations. This experience has reinforced my passion for the subject.
We've accomplished something remarkable together. Our journey has taught us the importance of applying our skills in real life situation and the achievable outcomes that can result.